So if we have dependent events A and B, what we need to do there is multiply, but when we multiply the event that depends on the other, we need to understand that its original has changed. We need to use the changed probability instead of the original. That is, if you want to find the probability of A given B, where in some sense B is affected by A, we have the probability of A times the probability of B given that A already occurred. And there's a special notation for that we'll see later. And for that matter, we can deal with this in the other direction, but you can just rename the things to make it fit what you have in mind instead. So let's get a couple of cases here to understand what we're looking at when we're talking about these ideas of dependent multiplication. For our first case, 2 cards are selected without replacing the first card from a standard deck of 52 playing cards. We want to find the probability of getting a queen and then getting a king. So, as we talked about earlier, as we should expect by this point, if we want the probability of getting a queen and a king, where importantly here we have those words without replacement, this means what we need is the probability of getting our queen as well as the probability of getting a king given that we've already pulled a queen, where it's not really that complicated, even though it's a longer notation. Again, we'll abbreviate that later, but this, hopefully we can tell, will be 4 out of 52, or if you prefer, 1 out of 13, while our second case will be 4 out of 51, which gives us a total value here without, so what I'm looking for here, reducing, of 16 out of 2652, or as most would prefer in a case like this, approximately 0.006. That is to say, it's very unlikely if you're playing a game of Texas Hold'em, you get a pair of king and queen in your hand. Regardless of what suit they are, it's not going to happen very often, which is why people might bet on a card dealt like that. But, well, I'm not going to say what that is again. Hopefully you get the idea. So, since we had a classical approach here of dependence, let's also take a more empirical approach as well for the sake of balance. For this example, 18,187 U.S. allopathic medical student seniors applied to residency programs and submitted their choices. Of them, 17,057 were matched with residency positions, where about 79.2% got one of their top 3 choices. Med students rank the residency programs in their order of preference, and program directors in the U.S. rank students. The term match refers to the process whereby a student's preference list and a program director's preference list overlap, resulting in the placement of a student in a residency position. Find the probability that a randomly selected senior was matched with a program and it was one of their top 3 choices. Where in this case, for the sake of saving a little bit of space, I'm going to let A refer to a student being matched and B being the student being matched given that the match was a top choice, because I've already had to say too many words here and I don't trust myself to write them as well. Where based on what we're given, the probability of A would be one of those 17,057 who did get into a residency position out of the 18,187 total students. Meanwhile, we're not actually told as much about the conditioning here, but there's an implication that it is affected because we're given that word given. For our second case, we have the probability that they match given that it was a top choice, is that percentage of about 79.2, written as a decimal there, where to get the value for the probability of A given B, I'm going to use some not A given B, excuse me, the probability of A and B. Too many words. Too many words. In this case, that's going to be these 2 values multiplied together, which is going to be kind of nasty, like I said, bad notation, but it's going to end up being approximately 73.4%, or 74.3, excuse me, 0.743. So it is fairly likely that if you are looking to be or currently a medical student, although generally med students don't take this class.
I got in! I got in! I got into Princeton! Yeah! Yeah! Woo!
Hey, I think that guy got into Princeton.
What makes you say that?
I don't know.
You'll get into the program you want. I don't know what the data says for nursing students, but hopefully it's similar. Anyway, that's our idea for dealing with the multiplication rule, but this is still a clunky notation, so let's talk about one way that we can more specifically refer to that, more cleanly refer to that, in terms of what's called conditional probability.